equations at the same time. And it should give you a set time is your third element, and it shows you orientation where you started as time progressed, as actually it's the t variable. It's not time in this case, it's just a t variable. It's not time until we use an application. But it's the third variable as t is progressing. Okay. Well, I didn't even hand it out yet. Yeah, but you can have it. Alright, as t is progressing, we can see what's happening to our graph. And here's your xy points in here. Okay, so this is in a parametric mode. Now, today what we're going to do is we're going to eliminate your parameter. And write this right on your homework so that you can actually see this happening. We're going to eliminate that parameter by substituting out for t from the first one, solving for t, which this one already is, and then substituting that into the second one. So this is already solved for t. So we're going to take this t out and replace it with an x. So you're going to get y is equal to negative 2x. And this puts us back into a rectangular mode. We call it a rectangular equation. And this, when you graph this in your regular calculator, will be that. So I'm going to check my mode, put it back into function, and put in negative 2x. And when I graph this, I get the same graph as my parametric. I get the same table, the same set of xy's, if you will. If you kind of look at, there's no t because I eliminated it. Parametrically, I can graph it with my parametrics, and I can eliminate it and make a nice little rectangular equation that you guys are used to. So kind of make a little bit more sense, right? The next one that you did, you also got a line here. You got a line from these two. Notice there's no exponent, so we're going to get some kind of a line here. And if we're going to eliminate this variable, we're going to solve this for t. It's not going to look very pretty, but we're still going to solve it for t. We're going to add 1, and we're going to divide by 3. You're going to take this, and you're going to substitute into the second, into the y. And wherever the t is, you're going to substitute in terms of x. So now my rectangular equation using xy will be 2 times and we can distribute this, we can get rid of the denominator, we can make this into a regular graph if you want to, or you can just kind of leave it like that, and we can graph it like this. You can come to your y equals, you can put it in just like you read it. You're going to need it, if you don't use your fraction bar key, you're going to need a separate set of parentheses, so I'll use my fraction bar. The fraction bar wasn't working before. Seems to be working now. So now watch what happens when I graph this. I get the same line as that one. When I look at my table, I get the same xy points. Not all of your xy points show up because you're in a t. You're based on your parameter. You're based on t. But like, for instance, negative 1, 1. Well, let me pick another one. 2, 3. There's 2, 3. 5, 5. There's 5, 5. See, it takes basically, because we had a setup. Our t was set up by a step. So it went by our t step instead of our x values. So you see how your t step, we set it up as t step of 1? That's where our graph came from. So of course that has an effect on where your xy points land on. But they end up with the same exact sketch. Okay? We kind of seeing this? All right. And again, as we go through this, you'll see the same thing. You've got some kind of a parabola here. because you've got a t squared. Now when we eliminate that, we'll solve this guy for t in terms of x. So we'll multiply both sides by 4, and we'll substitute this into this one. Do this on your homework paper. And lo and behold, you get a quadratic that is stretched because it's got a dilation of a factor by 16. So it's being stretched, and if you take a look at it, 116, there's one of the recognizable points. Don't forget your t-step went by 1. So that has an effect on your xy values. But if we plugged a 1 into here, your y would be 16. If we plugged a -1 into here, your y would be 16. And of course you can see your 0, 0. So if we were sketching it, it would look like this. It would look exactly like that. And you know, look on the 0, 0, my pencil. But that's what it's doing. It's pulling it, stretching it. All right, and again, you've got some kind of parabola again. You can kind of tell where it's off. It's off at the 0, 1. When x is 0, that probably should be a -1, or maybe it's a +1. 0, 1. So let's see what happens. We're going to take the first one. We're going to solve for t. And we're going to plug this into this. Okay, so we've got a horizontal shift to the right. So instead of starting at the 0, 0, it should start at the 1, 0. And we should see a 1, 0 there. And we do. So if you put this in your y equals, you'll get the same values as these xy's. Good? Guys, very good. Very good. Okay, and the last one, you also have some kind of a strange graph here. So we're going to take the first equation and we're going to solve for t. You can take the cube root, or because we're going to put it into something that has an exponent, I'm going to raise both of these to the 1/3, just so we get t to the 1. And we're going to substitute this into here. So we're going to get y is equal to 1/2 x to the 1/3 raised squared. So we're going to get y is equal to 1/2 x raised to the 2/3. And that will give us that kind of yes. Okay? So we can work with your parameters, or we can do them algebraically. Sorry about that. Okay, again, you're going to solve for t in your x equation. You're going to solve for t in your x equation, and you're going to sub it into your y equation. And that's going to give you one equation that we call the rectangular equation. We confirm these on your graphs, and we can confirm it with your rectangular equation. Now, sometimes we get some things that have a little bit of a domain restriction. And we can see from this that you have 2 domain restrictions. We're getting back to our domain restrictions. In the denominator, you cannot have a 0. So, if this is a 0, then t cannot equal -1, right? If t is equal to -1, this will give us a 0 in the denominator, which we cannot do. A radical in a denominator says, well, the radical says this has to be greater than or equal to 0. It has to be a positive number and that ends up in the radical. But because it's in the denominator, it can't be 0 as well. So we set this equal to greater than 0. And t is going to be greater than -1. So our restricted domain says t is greater than -1. Now, I'm not sure how much of that you have on yours. Let's see. I put part of it on there. You can kind of see by your table that it's starting at It started right after the -1. We can't do a -1, but I put a -0.9, I put a -0.5, just so that you would see that those have values. And that's where your XY values are coming from. So if you graph both of these in your parametric equation, I gave you the graph, you're really only going to see a little bit of a piece of this. For some odd reason, you're not going to see below it. Because it kind of like, we have to change your window a little bit. And then we're going to graph a rectangular equation. Now, I kind of gave you both graphs. To graph your rectangular equation, we have to take this one, and we have to solve for t. Not a pretty sight. But first we want to get rid of your radical. So we're going to square both sides. We need to solve for t, so we got to get t out of there. Now, I could cross multiply and divide out again, or I could take the reciprocal of both sides and get the t in the numerator. I can flip this one over. I can take the reciprocal of both sides. If I flip this over, this is t plus 1 over 1. And I don't really have to say the over 1. Subtract 1. And there is what we're going for. So notice where your equation is. So kind of we're heading here. So why don't I have that on my rectangular equation? Okay, we have to substitute this back into your equation yet. So we're going back into the y now. Bear with me. One step at a time. You have a t in the numerator, you have a t in the denominator. So let's plug into your t in the numerator. This is going to be 1 over x squared minus 1. Then you have a t in the denominator. And you still have a plus 1. So what happens to these ones? Cancel out. So you're left with this complex fraction. And you're saying, she's kidding. So we're going to take this, and we're going to find the common denominator. We'll put this over 1. Look at all your denominators. What's your common denominator? And what else? Factor of 1, and what other factor is down here? X squared. So if I multiply every term by x squared, I should eliminate my denominators. Out comes the x squared. I'm left with 1. Out comes the 1's. I'm left with x squared. Out comes the x squared. I'm left over 1. So here's my final equation. If you want to turn it around, there's your parabola. It's opening down. It's starting at the 1. And I don't know where my graph is, but your graph is starting at the 1, opening down. Okay? And it goes through here. And x has to be greater than 0, because we can't use any of these less than -1. Anything less than a t of less than -1. So sometimes they're not as pretty, but they still work. Okay, we saw it on your homework. They looked a little bit better. And where it gets really nice is for these guys. So we can sketch some of your comments on this as well. We can do ellipses, we can do circles. We just do those two, actually. When you set this in parametric mode, pull up your calculator and set your mode to parametrics. And watch what happens when you try to put your angle in. You're going to get 3 cosine. I go for my angle. That gives me where my t is. My angle is now my third parameter. My third variable. That's my parameter. And I put this one in here. 4 sine. Again, my angle is my parameter. when you do trig, notice where I set your window up for you. Your window your T has to go 360 degrees around, or we'll stop it and we'll show you that it doesn't actually go around. So your minimum is going to be 0. Your maximum is going to be, give me 360. If you keep it in degrees, 2 pi if you keep it in radians. Set your T-step to about 30 degrees. And I'll show you why in a minute. And we're going to go through this. Make sure your mode is in degrees. Otherwise, it's going to be messed up. And now just say graph. Now you get a funny looking kind of circle. If we zoom 5, you can see that this was an ellipse. Okay. Without zooming 5, what happens is your screen's a little distorted because it's wider this way than it is lengthwise. So it distorts it a little. The zoom 5 gives it a square look. So it kind of prints it out a little bit better. Now, here's a good thing to see for T-step. If I change my T-step and I only go to 300, watch what's going to happen to my ellipse. It's not going to complete. It'll stop at 300. Isn't 300 degrees in quadrant 4? Right? So if I stop my T-step at 180, it should only give me half of my ellipse. The T is what runs this. I think it's easier to see in an angle than it is on time. When we do an application, time will make a big difference. If we go to throw a ball and we don't give it enough time to hit the ground, it'll stop in the air. Because it's an application, you can see what happens to time. So when it's an angle, you actually can see if we stop short of the 360. So you want to make sure whenever we do angles, we go to 360. You can use 0 to 2 pi. Just make sure you set it in radians. Now, to take this guy and convert this to an equation for an ellipse, we're going to use these pieces. We're going to solve for your T. In this case, this is your T, right? Because we said your angle is a T. So we're going to divide both sides by 3. Thanks, Brianna. We're going to do the same for this one. Okay, thanks, honey. We're going to divide both sides by 4. Now, thinking back to trig, to sine and cosine, the one identity that we always used and we had to remember was sine squared plus cosine squared equals 1. So if we use this identity, doesn't matter what trig we added in, and we plug in the pieces now, we should be able to get some kind of a rectangular equation. So we're going to substitute this in place of this, but we have to square it. We're going to substitute this in place of this, but we also have to square it. And you can see what's happening. We're going to get x squared over 9 plus y squared over 16 equals 1. Isn't that the equation of your ellipse? And look before we squared it. Do you see over the y, it's 4? Doesn't it go up 4? On the x, it's 3. Doesn't it go over 3? So we can get to the equation of an ellipse through parametrics. You're all so impressed, right? Say, what else does she have up her sleeve? Can we do that with a circle? Yes, we can. We can do that with a circle. And so now we're going to amaze you and do that with a circle as well.
This going to make me money in the future?
Well, sure will. Sure will. These are all those little pieces of information that no one will know but you. Okay, so now we're going to do the same thing with your circle, but the circle has 2 little special kind of formulas to go with. H and K is the center of your circle, and R is the radius of your circle. So you're going to graph these things, and you can plug them into your H and K, and I realize you can quick cut to the chase and do your x squared plus y squared thing here, but we're going to humor me, and and we're going to plug these in. And H is your 3. R is always positive. And your Y for your parametric is your K. And your R, it's negative 3. Thank you. Thanks for catching me. I would graph this and say, hey. Okay, so now, you've got your 2 sets of parametric equations. If you put this in, your parametric, again, you have to go from 0 to 360. Yes?
Wouldn't the x be negative 3 because you just made the radius negative on the second one?
Thank you. Thank you. I can't talk and write at the same time. I just made the radius negative.
X equals negative 3.
X equals negative 3.
Y equals positive 1.
Oh, I have the whole thing backwards. Okay, let's start again. Oh my. Good thing I have you guys to check up on me. Thank you so much. Am I better now?
Yes.
Alright. So now, if you put this into your parametric mode, and I think we're still in here, according to this guy, we're going to plug this in, and we're going to see that this makes a circle. Okay, so we have 3. And the next one we had 1, 3, 9. Okay, and I think I set my thing back to 30. Yeah, and so there's a circle. Again, if you do a zoom 5, it probably makes your circle a little bit better. Yes. Where is your table in here, your mins and your maxes? And these are 30, so that's probably why. You can set these equal to probably even 10.
No, that would be negative 4.
Negative 4. Go 10 to 10. That's why. It's just on the scale. And when you do a zoom 5, it sometimes redoes the whole thing. And now if I zoom 5, it's just going to redo my thing anyway. Now, watch what also happens if I set my step to be very small. If I set my step to 5, watch what happens. Do you see it go a little slower? It's just going a little slower. This is where the T-step is more visible to see. The other one, it was too quick. We were just making a little line. It was too quick. If I set my T-step to 90, look how fast and how weird it looks. My T-step is fast, first of all, and it's not smooth. And that's the T-step that we have to play with. When we were just doing a little line, it wasn't making that much of a difference. Maybe the parabola, you saw it a little bit better, but in these, you definitely can see it. So you always have to find like a happy medium to graph these in. See again, we're still not getting a smooth circle. We got to drop our T-step down a little bit more. I usually find 30 works really well with the circle parts. It goes at a good speed and it makes it a little smoother. But you can play with your T-step. It's probably easier to see once you reach this point. Okay, now again, if we do this, we're going to take this first one and we're going to solve this for your parameter, which is this. We're going to add 3. We're going to divide by 3. We're going to do the same here. We're going to subtract 1. You can probably see what's happening here, right? We're going to divide by 3. Then we're going to combine these into one rectangular equation using your cosine squared plus sine squared equals 1. And you can see by your denominator that this is going to be a circle, right? Because they're both the same. So remember we said your ellipse is a special circle. So even though we're starting it like we would an ellipse, the denominators are going to be exactly the same. Here's your circle here. We started with an ellipse. We're going to square these out. There's your center. And the last thing you want to do, because you can leave it as an ellipse, or because it is a circle, multiply everything by 9. There's the equation of your circle. And again, you can see that your center is negative 3, 1. Your radius is 3. So we can take your parametrics and we can make it into one standard equation. Now, 1, 2, and test.